Lesson 7 is on balancing chemical equations. So we're going to talk about skeleton equations, understanding how to balance, and we're going to show you examples of balancing different types of reactions. So chemists use chemical reactions as a quick shorthand notation that conveys as much information as possible. So it's going to talk about the types of substances used or produced, the amounts of substances needed or retrieved. Think of chemical reactions as a method of good bookkeeping for chemists. So remember that the concepts discussed in chemistry follow a conservation law. We can't create something that wasn't originally there. So balanced chemical reactions will always show a reaction that satisfies this law. Without properly balancing the equations, the reactions will not take place as expected. So as we will learn, chemical reactions tend to have similar patterns to them. Because of this, chemists can also use them to help predict the outcome of reactions they are going to use. So here's an example of a skeleton equation. H2 plus O2 yields H2O. Looking at the example above, we see that hydrogen and oxygen do produce water. They're diatomic elements, which is why there's always 2 of each as a subscript. But you can see that it's unbalanced. The reason why is that there's 2 oxygen on the left-hand side in the reactants, but there's only 1 oxygen atom on the right-hand side. Again, conservation law states that we can't create something or destroy something. So if we have an extra oxygen atom in the reactants, we still need it to come out on the product side. So this is an example of an unbalanced chemical equation. It does not properly tell a chemist what is happening, nor does it properly tell us how much reactant is used to make the products.
So again, our skeleton equation is an unbalanced chemical reaction. When balancing equations, we must be using the coefficients. These are the numbers in front of a substance, also commonly called moles. We will be using these coefficients to indicate how many of that substance we used or produced. When no coefficient is written, as we see in all the examples above, for H, O, and the water, we assume that we only have one of that substance. For the example above, in order for it to follow the law of conservation of matter and the law of conservation of mass, which states that either mass nor matter can be neither created or destroyed, we must include coefficients to balance out the atoms of each element on both sides of the reaction. So the blank spots that we now have in our skeleton formula represent the areas where we're going to put our coefficients, which are going to be the numbers 2, 3, 4, etc., until we can balance both sides of the reaction. Step 1. Beneath the arrow, list the elements of the reactants and products. And what I always do is I just read it from left to right. So for the reactants, left to right, I list them below, H and O. To the list, I then include the number of each element for the reactants and products. I have 2 hydrogens and 2 oxygens of our reactants, so they go on the left-hand side. And I have 2 hydrogens and 1 oxygen, they go on the right-hand side. Those are your reactants, and those again are your products. I then add coefficients to the elements or compounds in the skeleton equation above. And when I do that, I will be changing the original math in the list below the chemical equation.
Make sure you do this at the same time. Do not wait until you've tried to balance out all the numbers first before changing those lists.
So when you look across my reactants and products, I'm already paired up with hydrogens, a 2-to-2 ratio, so I don't want to touch the hydrogens just yet. So let's look at our reactants. I have 2 oxygens on the left, but 1 on the right. So therefore, how can we make the number of oxygens equal? Oh, well, I can multiply that entire compound by 2. If I do that, I put that coefficient 2 there, that means I now have 4 waters and 2 oxygens. My oxygens are now balanced, but my hydrogens are off. I need to change something on my reactant side so I can get 4 hydrogens in total. You keep on changing these coefficients until they have balanced out the equation. I put a 2 there, and now when you do the math one more time, you'll notice that it's also a 4-to-2. So you have 4-to-4 hydrogens and 2-to-2 oxygens.
So just notice that you're allowed to change a balanced set already. It is okay because at the end, they will eventually balance out.
So the last step is to look at our coefficients, which means we have to simplify them. So when you look at our ratios, we have 2 to 1 to 2. In this situation of 2 to 1 to 2, we can't simplify that anymore, so we keep the formula as is. So the very last step is to relook at what you did, and you're noticing that 2H2 plus 1O2 gives us 2 waters. This is our balanced chemical equation. This is also a synthesis reaction, where two things are being added together to create one type of product.
So our next example is N2 plus H2 yields NH3. First thing you should notice is that this is unbalanced. The same number of nitrogens are not on both sides, the same number of hydrogens are not on both sides. So we're going to make those lists under the arrow. List your elements from left to right, N to H. Then tell us how many of each you have on both sides. So we have 2 nitrogens on the reactant side, 1 nitrogen on the product side. 2 hydrogens versus 3 hydrogens on the reactant and product side. Then we're going to add coefficients, and as we add coefficients to our skeleton equation, we're going to change the math of the list below. In most equations, it really doesn't matter which one you start with first, but it is very highly recommended that you never start with hydrogen first. So in this case, we're going to start with nitrogen, since that's the only other element. As you notice, on the reactant side, we have more than the product side, so I'm going to start by putting coefficients on the product side. I'm going to multiply it by 2 to get 2 to 6. Now my nitrogens match up. However, my hydrogens are still not quite the same. So I'm going to keep changing the coefficients until everything is balanced. I notice that if I put a 3 in front of the H2, I'm going to end up with those 6 hydrogens that I need. Now I have both sides of the reactants having the same amount of material. So it's a 1 to 3 to 2 ratio. If this is the simplest ratio, then I just leave the reaction alone. And it is. So this is my balanced equation, and this is yet another example of a synthesis reaction.
In this formula, we take potassium chlorate, and it's being broken down to make potassium chloride and diatomic oxygen. Again, this is not balanced. If you're looking at the oxygens, there's 3 oxygens on the left and 2 on the right. So step 1 is to list the elements of the reactants and the products, which we do here. We have K, Cl, and O. Then we include the numbers of each element. So I have 1 potassium, I have 1 chlorine, and 3 oxygens as a reactant. And I have 1 potassium, 1 chlorine, and 2 oxygens as a product. And then I'm going to change up, again, the coefficients so that way the math below can kind of balance out. So the only difference that I see right now is between my oxygens. So if I put a 3 here, that means I will now have 6 oxygens. And if I change on the reactant side, I'm going to put a 2 there, and now start to balance it out. So now my oxygens have been balanced, but the only thing I have to do now is balance out my potassiums and my chlorides.
As you see, whenever you put a coefficient, you're multiplying however many atoms of the elements you have in that compound. So it's best to find the least common multiple between the elements that are unbalanced, which is why we chose the 2 and the 3 subscript to begin with. So we keep changing. We put a 2 in front of the KCl to balance out the K and the Cl finally. Now we have to check those coefficients. 2 to 2 to 3. Is that the lowest ratio that we can get out of this? It is. So this is our balanced equation. What kind of reaction is it? Decomposition. You should have seen that from having one compound forming multiple little substances on the products. Polyatomic ions are still considered a single unit, just like elements. So, for example, when we're talking about silver nitrate, you would consider this as silver and a nitrate because we're talking about that ion as one whole unit. Aluminum carbonate, you'd have 2 aluminum atoms and 3 carbonate ions. For iron 3 nitrite, we're going to have 1 iron and 3 nitrite ions. Make sure they appear on both sides of the equation though. So as you can see here, we have silver nitrate plus copper yielding copper nitrate plus silver. You can see that nitrate is on both sides of the reaction, so we can keep it as one whole unit. So when we make our lists, we're going to keep nitrate as one whole unit. So make those lists under the arrows. Silver, nitrate, because it appears on both sides as nitrate, and then copper. We have 1 silver ion, 1 nitrite ion, and 1 copper atom, all on the left-hand side. On the right-hand side, we have 1 silver atom, 2 nitrate ions, and 1 copper ion. So the only thing imbalanced at the moment is the nitrate. So let's balance the nitrate. We're going to put a 2 in front of the AgNO3, and don't forget to change the list. When you put a 2 in front of there, you get 2 silvers and 2 nitrates. Again, it's okay to unbalance something that was originally balanced. Now we go back to the other side, and we have to fix what we just ruined by putting a 2 in front of the silver. Now everything seems to be balanced. Check that ratio, 2 to 1 to 1 to 2, can't be reduced. And then what kind of reaction is this? This is another example of single replacement because it's a single atom replacing another atom within a compound.
Now let's try some harder balancing equations. It may look like these are very complicated, but if you pay close enough attention, you will notice that we have an aluminum, we have a hydrogen, we have a sulfate, and we have a nitrate. The reason why is NO3 appears on both sides of the equation, and SO4 appears on both sides of the equation. So the first thing we're going to do is list out what are the 4 different types of species we have in our equation. Now let's add how many of each that we have. Now, where do we start? We never really want to start with the hydrogen, so let's try to balance out something that does not involve hydrogen. So let's put a 2, because I want to talk about my aluminums. Let's do them first. I'm going to put a 2 coefficient next to my aluminum nitrate. This now means I have 2 aluminums and 6 total nitrates. Okay, so my aluminums are now balanced and nothing else is. Let's go over to the other side and let's put a 6 by the HNO3. So now we have the same amount of aluminums, we have the same amount of nitrates, but now we have different amounts of hydrogens and sulfates. So where in our reactants do we have a hydrogen sulfate? That would be the other reactant, reactant B, let's call. So what times 2 is 6 and what times 1 is 3? Coefficient of 3. So when you put that 3 there, you now have 2 aluminums, 6 nitrates, 6 hydrogens, and 3 sulfates, which is balanced out with the other side. So this would be our final balanced equation, which is a 2 to 3 to 1 to 6 ratio. This cannot be simplified. So this is what we call a double replacement reaction. We're swapping out the positive metals with each other.